Okay, so now let's talk a little bit about calibrating the specific fragility function. So this will be a particular case of turning data into one of these functions. As we'll think about that log normal fragility function in particular. And the data we're thinking about, this is actual observations we've collected from empirical or analytical methods, right? We went out in the field and observed failures, or we ran computer analyses to get failures and non-failures. Okay? So the question is, if we want this fragility function, and we've got the IM specified, what we really need are the theta and the beta values. What are the numerical values of those for this function? So how do we take our numerical data and turn them into estimates of the theta and the beta? That's the question here. So one technique we can use that's pretty popular is maximum likelihood estimation. And so what we're going to do is we're going to find the fragility function parameters that have the highest probability of producing the observed data. So if the function was likely to produce that observed data, we'd say, oh, that's a consistent function with what we actually did observe. So let's just spend a couple minutes going more precisely on this. And I can point you to a more detailed look at this in a separate video as well. All right, so we'll get the field observations. That could be the empirical calibration or numerical analysis for analytical methods. We're going to have a set of IM levels, and we're going to count the fraction of observed failures at each of those IM levels. So that's our observed data indicated in the figure to the right, the circles. All right, so our observations take this form of this top equation. So observed probabilities of failure given IM equals, and I'll label it xj for kind of the jth intensity level. And so each j is going to indicate one of those circles at a different x-axis ordinate in the figure. And so the probability of failure, it'll just be the fraction of cases that had a failure. So we'll count how many failures we observed when IM equals xj, and we'll count how many observations we have. And we can call that kind of zj failures out of nj observations. And note, nj could be 1, right? I could just have one observation at that IM level, and this would still work. So we've got these failures observed, and then we've got the fragility function given in the bottom equation. And so what I need to do is I need to find a theta and a beta that are give me probabilities of failure consistent with the zj and the nj that we're looking at here. All right, I'm going to denote this probability here as p subscript j for IM equals xj. All right, so my function will work for any value of x. At that specific xj, let's call this probability p subscript j. Okay, so let's say if we knew pj for a given theta and beta value, what's the probability we would have observed the zj out of our nj observations? And so here we can think about these as Bernoulli trials. So each asset or each building of my nj observations had pj probability of failing. So the probability that I would see pj failures out of nj observations, that's going to be a binomial distribution. So this here is my binomial distribution probability mass function. Right? So this is when we've got kind of nj trials, each are independent, and we have probability pj of a success. So just a quick tour here. We've got pj probability of success. We saw that zj times. So we've got pj multiplied by itself zj times. We had nj minus zj non-failures. So whatever the rest of the observations were non-failures, those occur with probability 1 minus pj. And then there's different orderings of the successes and the failures out of the nj trials. So we've got this combination term out front, nj choose zj. That tells us how many different orderings of these failures and successes we could have seen out of the 20, or out of the nj observations. Okay, so that's a binomial distribution. And then we'd say, how likely is it that we would see zj observations given pj? We'll call that a likelihood function. That's the next equation down. What we can do is we can evaluate that likelihood function across all of the IM levels where we have data. So we'll take product. So we can take the product of that binomial distribution PMF over all the different IM levels where we had data. So we'll take a kind of a product over j. So the capital pi is indicating product. And then if we have m levels of IM, then we'll take the product from level 1 up to level m, multiplying all these probabilities together. All right. And then now remember this pj, we had just defined that as the probability out of the fragility function. So we'll just substitute in that fragility function here for the pj. And then when we add a 1 minus pj, we'll have a kind of 1 minus the fragility function here. Okay, so now we've got this likelihood that tells me how likely it is I would observe all that data over the different IM levels as a function of my fragility function. And as I change theta and beta, it'll be more or less likely that I observed all that data that I observed. Okay, and so we can think about trying to pick the theta and the beta value that maximizes that likelihood. And let's put that on the previous slide. Okay, so this is why the name maximum likelihood comes around. For each value of theta and beta that I put in this equation, I'll get some number out of this likelihood function. And I just need to vary those until I get the biggest value of the likelihood. So that's just an optimization or a search. Here's an example. If we've got this observed data out of those circles, I've got two fragility functions plotted here in the red and the blue. And so a fragility function just means a value of theta and beta. And so the blue one in particular has a higher median value out of this fragility function, so a bigger theta. But the red fragility function has probabilities that are pretty consistent with the observed fractions of failure that we saw from the observed data. And the PJs that come out of this red function are going to be similar to what we observed. So it's going to be more probable that we would observe that data. So that likelihood function will be higher. With the blue fragility function, the probabilities tend to be lower than what we observed. When I come to the different IM levels and I predict the probability of seeing these ZJs, the data, I would get a lower likelihood out of that blue fragility function. And of course, there's lots of other theta and beta values not plotted here, but we'll pick amongst them all. It turns out this red function is the one that maximizes the likelihood in this case, and you could see intuitively that would make sense. Okay, so that's the idea. The setup is through those sets of equations, and then there's lots of computer codes around that will do that calculation for you. I'll point you to one repository here where we've got some MATLAB and Excel implementations of that search.